Welcome everyone to the another session of the algebra geometry seminar. So today we are very happy to have Li Zhang from SUS Tech. So he will tell us about Kawamata-Morrison cone conjecture. Yeah, please.
All right. Thank you. Thank you very much for the introduction. And it's my great pleasure to give a talk at the National Taiwan University. It has been 7 years since my last visit, and I have a very beautiful memory there. All right, so my talk is about relative Morrison-Kawamata cone conjecture for Calabi-Yau fiber spaces, and this is the work partially joined with Hang Zhao. So let me first briefly recall the setup. We have a Calabi-Yau fiber space. So I will write the CY for aberration of Calabi-Yau. And this consists of 3 parts. We have a fibration, means it's a surjective map with connected fibers. And then we have the Calabi-Yau condition. So this is the Calabi-Yau condition. Means the canonical divisor is trivial relative to the base. And people sometimes put other conditions like the vanishing of higher cohomologies, but from perspective birational geometry, I only impose the non-trivial of triviality of the canonical divisors. So this is my Calabi-Yau condition. And certainly I require some singularities of the space. So it could be singularities, but you can just think it's smooth. So we're assuming it's smooth. These are the 3 conditions for the Calabi-Yau fiber space. And I also assume the minimum model program and abundance conjecture throughout this talk. So let me briefly remind you what I mean by minimum model program. That means if you have a variety X over S, there is some birational morphism or birational map such that KY is NF. And the singularities of Y is better than X in terms of discrepancies. So this is the minimum model program I was using. And another part is abundance conjecture. This basically means the following: if KY is NF, then is semi-ample. Then KY is semi-ample. But if you are not familiar with these terminologies or results, that's okay, because it's just using implicitly in the theorem, so it won't affect your understanding of the whole talk.
Well, do you assume MMP for K or just K? Because most of the cases.
Sorry, could you repeat your question?
Because your context is like Calabi-Yau, Calabi-Yau fiber space, and so do you?
Oh yes, I understand. So I assuming MIP for the pair actually, because I need to perturb my divisors in some effective cone. So I need to somehow perturb my divisors. So I indeed require minimum model program because I'm working with pairs. But even if I'm not working with pairs, I also need to using this minimum model program. I will point out where this is used. Yes. Okay, then we use some notations. So suppose D is a Cartier divisor on X, and we say D is movable over S. This just means the base locus of this linear system, of corresponding linear system. So let me denote the base locus. So to be the intersection of all divisors D prime linear equivalent to D, and D prime is effective. So this is the intersection in terms of set. And we assuming this base locus has codimension higher bigger or equal to 2. So I use assuming base locus of this linear system of OS bigger or equal to 2. So the fixed part is very, very small. This is the meaning of movable divisors. All right, let me mention an example of movable divisors. Suppose we have a birational map, which is isomorphism in codimension 1. This means the two maps, we have a birational map, but the discrepancy of, where they are not isomorphism has codimension bigger or equal to 2. So it's very, very small set, they are not the same. And suppose we have a base point free divisor Y. This is the base point free divisor on Y. And then I let AX to be the strict transform of AY. You just take the strict transform. And then the claim is this AX is movable. The reason is very simple, because AY is base point free. So except the part where the two varieties are not isomorphism, this AX is also base point free. But the place where they are not isomorphism has very large codimension. So totally, it's movable on this variety X. And the same argument applies if you replace AY by a movable divisor. So if AY is a movable divisor, two varieties are isomorphism in codimension 1, then the strict transform is still movable. So this is a simple fact. It turns out, basically, the minimal model program of Calabi-Yau variety will tell you this is the only way you can get a movable divisors. All right, next ingredient are some cones for varieties or fiber spaces. So first we define this Néron-Savary group. So it's a Picard group. We take the group of isomorphism Cartier divisors, and then you model out the numerical equivalence. So numerical equivalence means the two divisors have the same intersection with curves. And this is Néron-Savary group. Although the Picard group would be very large, this Néron-Savary group is always a finite dimension or finite generated group. And then we want to get a moduli space, we tensor it with real vector space, so it becomes a finite dimensional vector space. And the cones are leaves inside of this vector space. This cone is called the effective cone. So I said effective cone. This is a cone generated by effective divisors. Basically, this means we have a effective divisor. We consider this its class inside of Néron-Savary group or vector space, and then we consider the cone generated by it. So this cone is just simply a naive understanding of cones. All right, and the next we consider movable cone. This is a cone generated by movable divisors. So movable divisor is where I define here. It's movable. The linear system has very small fixed part. But these cones could be very complicated. For example, it may not be closed, and it may not be polyhedron. Means it may not be generated by finite rays. It could be something like a round cone, or some part is round, some part not. The project about this Morrison-Kawamata cone conjecture is to understand the shape of this cone, or using convex geometry to understand the birational geometry. So the last ingredient in this theorem or in this conjecture is birational group. So I'm using this BIR X over S to denote the birational maps from X to itself over S. But there's one more condition. I require this morphism is isomorphism in codimension 1. G is isomorphism in codimension 1. So this is the actual requirement besides this birational. The reason we require it is from the following. So if we have isomorphism in codimension 1, and if D is a movable divisor, D is movable, then we take the strict transform of D, it is still movable. Well, this is our previous example, right? If you have a two variety isomorphism in codimension 1, you have one movable divisors and the strict transform would be movable. So this is the reason we put isomorphism in codimension 1 upon birational isomorphisms. But this condition is automatically satisfied if X has good singularities, say if it's smooth. So it's not too much requirement. So it is automatically satisfied if X is smooth. In other words, if X is smooth, it suffices to require the map is birational. Okay, so because this reason, we know this birational group acts on the movable cone just by proof forward. So if you have a movable cone, then we have the map still lands in the movable cone just by G, comma D, and this is the push forward. So I also denote this push forward by G times D. Well, with these three ingredients, we are able to state a cone conjecture. So this is a statement of cone conjecture. And we are working with the Calabi-Yau fiber space. So let the X over S be a Calabi-Yau fiber space. Then the conjecture predicts there exists a rational polyhedron cone inside a movable cone such that this pi is a fundamental domain under the action of a rational automorphism group, as I mentioned before. And the second part of the conjecture is this Calabi-Yau fiber space only admits has finite minimum models. So by this, I mean the following. So we consider the set of Y over S, and they are isomorphism, they are birational, I mean. Also, KY is linearly trivial over S. So we consider all such varieties, and the number of such varieties are finite up to isomorphism. So these are statements of this cone conjecture. Let me explain what I mean by fundamental domain. So by fundamental domain, I mean two things. First, it has to fitting up the whole cone under the action of birational group. So we require under the action of birational automorphism group, this cone filling up the whole movable cone. And secondly, I require they intersect only on the boundary if they are not the same. So if we take the interior of this rational polyhedron cone, then it intersects with the whole cone empty, except they are the same. So it is what you can imagine. Suppose your cone is round, but you have some rational polyhedron stuff. This is a section of the cone. I look from the top. Then you can filling up this round stuff by this polyhedron cones using the rational automorphism group. Filling up this cone in the way that they only touch the boundaries. Two different cones only touch the boundaries. So the idea is to using some convex geometry to understand the birational geometry of Calabi-Yau fiber space. And I would remark that this is just one part of the cone conjecture. It is about movable cones. There is another part of the cone conjecture, Morrison-Kawamata cone conjecture, for Nash cones, and the group is automorphism group instead of birational automorphism group. So this is I just stated one part. And there are many generalizations of this conjecture. For example, you can work with KLT Calabi-Yau pairs. That means you can stick with a variety together with some boundary divisors such that this pair is linearly trivial over S. You can also modify the statement for such varieties. And thirdly, there are some minor variations on the choice of the cones. So sometimes you working with a movable cone, sometimes you want to add something more, but exactly they have the same closure, but at the boundary you have some other choices. But I don't want to go to the details. Basically, my feeling is on the choice of the cone is, it is what you can prove, then you're using what the cones you want. But sometimes if you didn't choose the correct cone, you will not get the desired result. I mean, the whole point is to study, the whole goal is to study the birational geometry. If you didn't choose the correct cone, then you may not get the consequence about, you get the desired consequence about the finiteness of models or some other things. I will mention this briefly later. So these are the statements, and let me recall the history briefly. The conjecture start with Morrison, who formulated this conjecture from mirror symmetry, from some mirror symmetry consideration. But later, Kawamata took the point of view of birational geometry and reinterpreted this conjecture for more fibrations, and he established the result when the variety has dimension less or equals 3 and fibered by surface or curves. Later, Totaro established for KLT log surfaces, and Lajic Pinel for Picard number 2, and the birational group is infinity, and also very recently, the conjecture has been proved for elliptic fibrations. And also, we have some strong evidence for special varieties. For example, it's a Glasgow result for K3 surfaces. And another large class of Calabi-Yau coming from the anti-canonical linear system from Fano varieties. So if you have ambient space to be a Fano variety, you consider the linear system. Suppose it's non-empty, you take some general element in this linear system. This X is Calabi-Yau. And people want to examine the conjecture for such Calabi-Yaus, but it turns out it's still not known for general ones. For example, if P is the product of P1, it has been exemplified clearly. And if you consider some other projective spaces plus some other conditions, it could also be proved. And then P could be a Mori dream space from plus other conditions. The anti-canonical Calabi-Yau hyperplane can be also satisfy the conjecture. And if you take P to be some vector bundles, then you can also establish the certain result. Also, the result is known for abelian varieties in any dimension, and for hyperkähler varieties with some restrictions. But in this case, the cone is slightly different. So this is a version not very compatible with the birational result, because their choice of cone are not exactly the same as what I mentioned before, or people desired. And also for Schoen varieties, actually generalize the Schoen varieties. Also, the conjecture has been classified for the variety over non-algebraic closed field or positive characteristics. For example, for K3, it has been established for non-algebraic closed field and certain, I think, not equal to 2 or something. And for irreducible simplex varieties as well. So basically, my feeling is there are many sporadic examples to support the conjecture, but it's still lacking for strong evidence in higher dimensional case. For example, for dimension 3, this is wide open. And if you are interested in the history or the result, you can look at the Nice Way by Lagigi, Ogu, and Pinel. So I'm put here. All right, these are basically background materials and review of history. And now it comes to say some result I want to present. So the first result I want to present. So if there is a rational polyhedron cone pi inside of effective cone, such that under the birational action contains the movable cone, then the cone conjecture holds. So this is the first result I want to present. Recall the cone conjecture is about the movable cones. So this is a movable cone somehow. And the conjecture says there are some rational fundamental domain inside of movable cone. But now this result claims it suffices to find a cone inside of effective cone. That means this is a rational polyhedron cone generated by effective divisors. And if this effective cone is choose nice enough such that it can cover this movable cone, then you can cook up from this pi to get a rational fundamental domain for the movable cone. So this seems a little simpler, but it's still very, very difficult to find such cone inside of effective cone. Okay, so let me I will prove this result, but let's focus on the second part, the finiteness of middle models. The reason is the first part can be proved similarly. The existence of fundamental domains can be proved similarly, combining a result of Lui-Jingga.
Sorry, could I ask a question?
Oh, sure, go ahead.
So if the base S has a positive dimension, then in general, the effective cone could contain some non-trivial linear subspace, right? Or
yes,
yes,
exactly. Yes.
Yes, but Roenga's result seems to be so about strictly convex cone or
Exactly, exactly. Yes, that's a good point. And yeah, so for example, if you consider a contraction, then this could contains a non-trivial vector space, right? So in order to apply Lui-Jingga's result, you need to modular out this maximal vector space. Then you project your cone. So suppose there is some lines or some vector space, you just project it to this maximal vector space, and then your cone become non-degenerated. But this will also give you some problems. I cheat a little bit here on the fundamental domain. You see, I mentioned that the fundamental domain is here, but some people also require the following. So other people also require, if they are the same, then G has to be the identity. But because I model out maximal vector space, I cannot make this requirement. Because somehow this G could be act non-trivially on this maximal vector space. But after I lift it up, although this condition is satisfied, but G is not identity. So you have to pay something if you want to apply Lui-Jingga's result. That's exactly what we did here. So we have to model out the maximal vector space to reduce Lui-Jingga's result, and then I lift it up. But then in this process, I lose something.
I see. Thank you.
Yes, thanks. Okay, so the result basically says it suffices to consider some cones, rational polyhedron cones inside of effective cone. And this is a philosophy I want to emphasize throughout this talk. So the cone conjecture, you could only consider effective cone, elements generated by effective divisors. Okay, so we will present a proof for the finiteness of Minion models. But before the proof, we need to recall a big result, which is about the Shogorov-Toddy. So this is the result of Shogorov-Choi. And this result will assume abundance. We use it here. But I only state the result in our setting. Their result is for general variety, but we state for Calabi-Yau varieties. So let X S be a Calabi-Yau fibration. And we consider a rational polyhedron cone inside of effective cone. Rational polyhedron cone. Their theorem claims there exists a decomposition of finite polyhedron cones, rational polyhedron cones. There exists a decomposition of finite decomposition of rational polyhedron cones. such that if two divisors, arbitrary two divisors, satisfy their class lives inside of the same decomposition, and if one of them has a minimal model, then the other one automatically D be the minimal model. Is also a minimal model. So let me explain this. Suppose we have P. This is the rational polyhedron cone. And then there exists the decomposition of this P to some smaller polyhedron cones. The result is if you can find two effective divisors lives in the same cone, for example, maybe this is better. If this cone, so two divisors, this is class B, class D, lives in the same cone. And for example, for P, you have a minimal model. That means ky plus by is NAF. Maybe address it here. Because X is Calabi-Yau, so ky is also trivial. So this by is trivial over S NAF. And then the corresponding divisor D, you consider the same variety, but you push forward the divisor D, you get ky plus dy, which also linear equivalent to dy over S, is also NAF. This is a result of Shogorov and Choi in our particular case. So in other words, this means the cone shares the same minimal model. Divisors. So the consequence upshot is divisors in the same polyhedron cone Pi share the same minimal model. If it is a minimal model for one divisor, it automatically be the minimal model for the other divisor. Okay, so this is the rough idea of this theorem. And because in our case, we are in Calabi-Yau case, the minimal model just means the divisor itself is NAF. All right, with that, we can prove theorem 1. So we will prove the theorem 1. And let's recall what we want to do. The assumption of theorem 1 is the following. We have a rational polyhedron cone inside of effective cone. And under the action of birational group, it contains a movable cone. Right? This is our assumption in theorem 1. And the goal is to prove the following. We want to show X has finite minimal models. So we want to construct a finite minimal models such that one of minimal model of X must be corresponding one of them. Okay, then how should we do? We apply Shogorov choice result theorem to P, we know this can be decomposed into finite rational polyhedron cones. And the divisors for each cone share the same Minu model. So suppose that means for Pi, we can corresponding to a Minu model of we can consider a birational map x to yi such that if D inside of P, then this one is a Minu model. Right, let me just quickly recall what I'm doing here. So we have a decomposition of this rational polyhedron cone such that for each cone, divisors lies in the same cone share the same Minu model. So this Minu model only depends on the cone Pi instead of divisors, because all the divisors share the same cone. So for this Pi, I take a Minu model yi. Okay, this is the Minu model corresponding to Pi. And because this is the finite decomposition, so we get a K of Minu models. We have K of yi. And I want to show if X has a Minu model, it must be one of yi. So let me take a Minu model. Then we can do the following. So this is the Minu model. We take A to be AY to be a very ample divisor on Y. Okay. And then I take the strict transform. So AX is the strict transform on X. For example, for simplicity, we're assuming these two varieties. So assume the isomorphism in codimension 1, also in include 1. Oh, actually, in my talk, I did not give a complete rigorous proof, but I just want to convince you this will work. So you think of it hardly, at the end of the day, you will figure out yourself. So I don't stick to very rigorous statement. And sometimes if the simplification would be simplify my statement, I will just stick to it. So we take the strict transform, these divisors, and by the first example I mentioned, this AX is movable. Right? You have very ample, it's space point free, so you take a strict transform, it's movable. Well, this AX lives inside a movable cone. Actually, it's class, but I just write it this way. And what we have is this movable cone is contained in the birational group action on our P. This is the assumption. So it implies there must be some divisor, say B inside of P, and some G inside of birational action, such that this AX equal to G times B, right? And because this B has been decomposed into part, so without loss of generality, we're assuming it lives in P1 just. Okay. So we can assuming this divisor B lies in P1. And under the action of G, it is equal to AX. Now we put this together. Oh, recall this P1 also corresponding to a variety, which is Y1. And the good thing about this Y1 is if you take the strict transform, this is NAF because it's a Minu model. So this is NAF. Now we can put this together. So we have this original X. This is our Y. we have a divisor AY here, the strict transform AX here, and we have action G. So this is a G action. And there are some, so maybe this is the direction I should write, because this is our B, right? From here you have G inverse AX equal to B. So this is our, so some direction. You don't need to this one. So you have G times B equal to AX. And then you have some Y1 here, such that BY1 is NF. This is ample. This is NF. So you compose these birational map from a divisor, from an ample divisor. Under some birational map, you get a NF divisor. And if you're assuming something more, suppose this is a theta. Theta is ISO in code measure 1. And the Y1 is Q factorial. These two conditions alone will imply Y1 is isomorphism to Y. So this is a standard argument, just consider some common resolution, and then you consider the contraction curves. So we see Y is isomorphism to Y1, but there are only K of them. So we show the finiteness of models. So this implies finiteness of model. So don't be bothered by these two conditions. These conditions could be achieved. You do some Q factorizations, you do some small modifications, you can achieve this. And then you also need to control the contractions, which could also be done. So this is the essential idea to prove the finiteness of models, and it has been well known, for example, in BCHM. So you can using the finiteness of cones to get finiteness of models. So any questions about this part? All right. So I want to emphasize again, we should focus on cones inside of effective cone rather than working on movable cones. All right. So this is finance part. So the upshot is we should consider some inside of effective. All right, next goal is we want to show cone conjectures of fiber space follow from the cone conjecture of fibers. So, I mean the following. If you consider some fibers and you want to get a cone conjecture for the whole space. So what fibers should I mean? Ideally, we should working with geometric fibers. That means you take a generic point of the base, and then you passing to the algebraic closure of this generic point. The advantage is we are still working in the algebraic closed field, and somehow we can reduce the dimension. But there is a key difficulty if you want to working with geometric fiber. The problem is the connection, we cannot get, I mean, it's not very clear. It's clear to get how the birational group. Let me put this way. So theoretically, we know how to get the birational group from the geometric fiber. But if you just given a birational automorphism group of generic fiber, geometric fiber, you cannot literally corresponding to a birational automorphism group of this fiber space. So put it simply, this just means the connection between these two birational groups is not that simple. Even if you can prove the cone conjecture in this setting, because the birational group are changed, you're using different birational group, you cannot get the statement for the total fiber space. So we are cheating a little bit. Momentarily, we're working with generic fiber. The generic fiber automatically tells you the birational automorphism group of generic fiber is same as birational automorphism group of the total space if the singularities are good. But the price we paid here is we have to working with non-algebraic closed field, which is not something very comfortable. So we are working in the generic fiber, and we should also formulate the cone conjecture in this setting, but it is exactly the same. For example, if a divisor on this generic fiber is movable, if it will pass into the algebraic closure is movable. This could be checked very easily. Or you can just take this for the definition. Now we state the second theorem along this line. It says, if the cone conjecture holds for the generic fiber, for the movable cone of this generic fiber, then it also holds for the total space. So if you have the statement for the generic fiber, you can prove it for the total space. And this is proved under the assumption of abundance, but we can get an unconditional result. Hence, cone conjecture holds when dimension is less or equal to 3. Less or equal to 2. If the radial dimension is less or equal to 2, this could be proved unconditionally. The reason is we have two parts. So this, the cone conjecture for surface over non-algebraic closed field is known. So this is known. This is known by Kawamata. And the abundance we assume actually only require we only need to assume abundance for the generic fiber. General fiber. So it's relative dimension 2. The abundance is also known. We only need to assume abundance in the relative dimension case, relative dimension 2. So you don't have to assume abundance for the total space X, because it could be derived from the abundance for the fibers by a result of Heiken and Xu. So unconditionally, we can prove relative cone conjecture for surface fibrations. All right. So now I want to give a proof in this case. Okay. So our is we know the cone conjecture for the generic fiber, and we want to prove for the total space. So let me first prove this for the simple case. By simple case, we mean the following. If we have two divisors which are numerical equivalent over S, then it's linearly equivalent to S. So this is a simple case. We're assuming this. Assume this. The inverse direction certainly holds. If they are linearly equivalent, then they are numerically equivalent. But the numerical equivalent generally does not imply linearly equivalent. But for the moment, we're assuming this simple case and prove it. This is not very difficult, and is pretty much the same as the previous case. All right, so by cone conjecture, for x eta, this is something we assume. We know there is a cone, rational polyhedron cone, such that inside of effective cone, such that birational group act on it contains movable cone. Okay, I only using this weak version. The strong version is we have a cone which equal to movable cone, but I only using this weak version. This is something I emphasize. We should consider effective cone, and we don't need to working with they are equal. You can just require under the action of birational group, it contains a movable cone. So I only using this version. And we take a movable divisor in the relative case, and then we passing it to the generic fiber. This is still a movable divisor, but for the generic fiber. And because of this condition, it implies there is a G for the birational automorphism of generic fiber, but this is the same as the birational automorphism of the space, as I mentioned before. And another divisor, say B, inside of P8. Let me just write B8, such that G times, let me write here. Sometimes G times B eta, the class, equal to D8 inside of this movable cone, right? Because of this relation. We just rewrite it. And recall, this is a cone we are working with Narain-Savary group. This relation just means the two divisors are numerical equivalence. By our assumption, numerical equivalence implies linearly equivalence. So by assumption, this implies the two divisors are linearly equivalent. So this is the place we're using the assumption. From numerical equivalence, you get linearly equivalence. And because the two divisors are linearly equivalent over the generic fiber, this just means the two divisors are linearly equivalent. I mean, I'm using Q or something. Linearly equivalent in the total space modulo out some vertical divisor. Right, this is the fiber space over the generic fiber, over some generic fiber, they are linearly equivalent. They are also linearly equivalent in the total space if you properly add it into the vertical divisors. So this is what I write here. They are also linearly equivalent over S, I mean, modulo some vertical divisors. Okay. Now we consider a cone. So previously we have this rational polyhedron cone. You can think of this rational polyhedron cone coming from it just coming from a cone inside of this N1, or maybe I just write EFXS, and you take the corresponding generic point, you get this rational polyhedron cone. So we just lift it to a rational polyhedron cone inside the effective cone. But now we consider something larger. We define this cone to be P plus a linear space. This is a truly non-trivial linear space plus vertical divisors.
Sorry, could you explain again what do you mean by lift of the polyhedral cone?
Oh,
yeah. So how do you define this P?
Yes, yeah. So So this is a rational polyhedron cone in this, let me just write here by lifting. So in this space, we have this P8 is generated by divisors D8. Let me write cone here. So this is a cone generated by these divisors. This D8 is effective because it's a rational polyhedron cone inside of effective cone. And then you just take the closure. This would be an effective divisor on, for example, on the total space. Then we just consider the cone, which is defined by this closure. So let me just write DI to be this one. Yeah.
Okay.
Then this would be a cone inside of effective cone. Yes. Yeah. So we can just consider some effective cone lives inside of the total space, and then I consider the whole vector space. I really want to R, not R plus, not R positive part. So this is a vector space, non-trivial vector space. And because there are only finite vertical divisor classes, so this is also, this is a rational polyhedron cone. Polyhedron cone. Of non-degenerate. Degenerate, okay. Yes.
And not necessarily inside the effective cone.
Oh, this is also, yeah, that's a good point. This is the point I want to make. For effective divisor, for vertical divisor, vertical.
Oh, yes.
No matter plus minus is always inside of this effective cone.
Yes.
So this is the advantage we're working in the relative setting. You can freely throw in the vertical part. So the reason is, let me just explain. We consider a simple case. If we have F1, you have F2. Suppose these are fibers over a curve or something like that. And you know this F1 or plus F2, maybe some multiple is trivial over the base. So automatically F1 minus F1 is linearly equivalent to F2. That means it's also effective. So the advantage for vertical divisor is you can freely add a plus minus sign before it. You will always get an effective divisor inside of the relative cone. So after these operations, we get a rational polyhedron cone, but also lives inside of effective cone. Yeah, let me just move down. We get this one. And now I claim under the birational action of this larger cone, it contains the movable cone of Bx over S. So for example, we only need to consider D because D is arbitrarily chosen from movable cones. So the reason is the following, right? We have G times B linearly equivalent to D plus some vertical divisors. F is vertical. Although it may not be effective, it could be plus minus vertical divisors, but we know it's effective in the relative setting. So we have this, and from that, because these vertical divisors, no matter its plus or minus sign, are always considered inside of this, always included in this P tilde, because we include all P tilde here. So this part is contained inside of this birational group action of P tilde. For example, this could be right here, like G inverse action of F plus B. And this part lives inside of my P tilde. So we have a group action on this on an element inside of a rational polyhedron cone, which equal to D. Because D is arbitrarily chosen, so we have this relation, right? And because of this relation, we can apply theorem 1 by theorem 1. we know the cone conjecture holds. So this is the advantage for the fiber space. You can check on the generic fiber, and the differences could be just lies in the vertical part. But the vertical part are always effective. So you can freely throw, no matter plus vertical or minus vertical, no matter which coefficient you are choosing, it's always effective in the relative setting. So you can freely throw in all these discrepancies. But all these argument lies in this fact. We get a linear equivalent on the generic fiber. I mean here, we get linear equivalent on the generic fiber. However, it may not always hold in the general setting. So let me state the general case. And the idea to deal with this case, back to Kawamata's, the first paper I mentioned, but I feel that there are something off in his argument. So let me explain the idea I'm putting here. So what's the key difficulty? Let me see an example and to explain the key difficulty. So we consider E1 and E2 are general elliptic curves. So you don't need to know what general mean, elliptic curves. So they are the same curve, but I denote by E1 and E2. And then I consider a surface, a Abini surface, which is a product of these two curves. And by the general elliptic curve, this would be tells you this one has dimension 3. The Néron-Savart group has dimension 3. And the generators are the following. So this one is generated by, say, E1 times 0, 0 times E2, and a diagonal. So this is diagonal. So let me draw the picture. So we have E1 cross E2, and suppose this is E2, this is E1. It's generated by one divisor, one curve, another curve, and a diagonal. Okay, now we can enter the fibration, the Calabi-Yau fiber case. So we can just consider this Calabi-Yau fibration. This is my X. So in this case, because E2 has Picard number 1, so the relative setting has Picard number, dimension equal to 2, right? And this relative Néron-Savart space is generated by this horizontal part. Horizontal part should be 0, E2, and the diagonal. Right, the total space without over base, it has dimension 3, and over a base dimension cut by 1, so relative dimension is 2. And the two generators is a horizontal divisor and a diagonal divisor, right? So but be careful, in this case, we do not have, in this case, F, let F be a general, let F be this should be a generic fiber, but let's make it simple. I just consider a general fiber, or general fiber, whatever. But in this case, on this fiber, numerical equivalent does not imply linear equivalent, because this F is just an elliptic curve, right? It's an elliptic curve. Numerical equivalent on F no longer implies linearly equivalent. So let's do the restriction. we restrict to the fiber F, and we see delta F is the same. Let me just write this by T. This is a section, horizontal section. So T restrict to F. They are linearly equivalent because this is 1 point. This is a 1 point. This is a section, so this is another point. The degree are just 1. Certainly, they are linearly equivalent. However, the two divisors are numerical equivalent. They have the same degree. However, the two divisors are linearly equivalent if and only if they are the same. Right? On an elliptic curve, the two divisors are only linear equivalent, only they coincide, right? So in this case, they are not the same. But why this causes trouble? The trouble is the two divisors, T and delta, looks the same on the generic fiber, or they are the same element in this movable cone of this generic fiber, or Narayan-Savary group of generic fiber. But they are indeed quite differently. They are not the same for the total space. Even modulo the vertical divisor. Because in our case, there's no non-trivial vertical divisor. I mean, all the vertical divisors are numerical equivalent trivial, so this is nothing. So you see, you cannot tell the difference on the generic fiber. So this is the key difficulty. I'm not sure if this makes sense. So it could happen that two divisors look the same on the generic fiber in the fiber space, in this total fiber space. So the difficulty, let me summarize here, is we cannot see divisors on the generic fibers, on the fibers. So we cannot tell the difference. They are the same on the fibers, but they are indeed quite different on the total space. Then how should we figure out this problem? How should we handle this? Well, look at our case. We are in the elliptic curve, right? We have two divisors, or 2 points. And there is a group action on this elliptic curve. We can move one divisor to the other, and they are the same, right? So this is 1 point, this is another point. There is a group action, there is a alpha inside of E, such that we can just move this divisor equal to the other divisor. This is a group action. So we can translate one divisor to the other. Okay, and they are the same. So certainly they are linearly equivalent. So let me formulate another way. Because this group action coming from an automorphism group of E. So this is the same as E. And this means we have a group action on this divisor. We get a linearly equivalent to the other divisors. So we have two divisors which are numerically equivalent in the generic fiber. They may not linearly equivalent, but under an action, they are linearly equivalent. This is a group action, certainly automorphism group, so it certainly lives in the birational automorphism group. This action is allowed in our theorem, right? We could allow some birational action on this polytope contains the movable cone. So it fits well in our case. We allowed in this action. They don't have to linear equivalent literally. You can do some modification to make they are the same, a linear equivalent. Okay, so this is the idea to fix this problem. Although it looks quite special in this case, but it turns out this idea could be moved forward for the general case, even for pairs. So let me explain how to do generally. Okay. So we using some group action to fix these non-linear problems. Okay, so let me give you the details. Okay. So let me come to the details how to fix this problem. Again, we consider a divisor in this movable cone, and we take the generic fiber. It lives in this movable cone of generic fiber, and by assumption, because we're assuming the conjecture holds for generic fiber, there exists a rational polyhedron cone. This is a rational polyhedron cone. Lives inside the effective cone such that you can take a G in this birational action and a B lives in this cone G B eta numerical equivalent to D eta. So we only know this numerical equivalence. And now our goal is to enlarge P eta to some new cone P eta tilde, a still a rational polyhedron cone, such that birational action on P eta tilde, I'll just let me, because there are some we need to enlarge B to some cone depends on B, such that this birational action on this B tilde will contain D eta. This is similar as before. Before we enlarge cone by throwing in all the vertical divisors, but now we need to do something slightly different. But still, we need to enlarge this to a polyhedron cone, such that under this action it contains D eta. So this is our goal. And then you can do this for all the divisors. Now we just did this for B, but you can think you can do this for all the divisors for P because it's a rational polyhedron cone. So there are only essentially finite divisors generated by finite divisors. Okay, how should we do this? We're using similar ideas, but we need to work in some new stuff. We consider automorphism group of this generic fiber. So I'm not doing this very rigorously, but this is how I think of this. So we consider the automorphism group. This is an algebraic group, but we consider the identity element. So if you don't know this, we can think of this as the automorphism of this X eta, which is deformed from identity continuously. So what I mean is you have identity map, and then you just change it continuously, you get an automorphism group. You got an automorphism. So how should we think of change continuously? We should change it along some vector field, right? You change one point along a vector field to another point. So this is some change or deformed along some vector field. Along some vector field. Therefore, this can the dimension of this can be computed. The dimension of this is equal to the dimension of the vector field, whatever it means. The dimension of tangent space. And by the Calabi-Yau condition, you're using certain duality, you will see this is equal to H1 x eta O x eta. You're using Calabi-Yau condition, using Serre duality, Hodge duality, you get this. Okay. Certainly here, there's does not make much sense about Hodge duality, but you can make this rigorous. There are some not very difficult arguments to make it rigorously. All right. Also, because this element change from identity continuously, so it preserves the numerical equivalence. Well, you can think of numerical equivalence is about the intersection with curves. It changes continuously, so the intersection number cannot jump. So if for any divisors, after under this action of automorphism group, they have the same numerical equivalent class. So it keeps the numerical equivalence. All right. And now we should consider another group, which is Picard zero. This is a group parameterize all the divisors which are numerical equivalent to 0, modulo the torsion. So Picard zero are these are just the divisors D, such that D is numerical equivalent to 0, model some torsion. This is also an algebraic group. And this Picard zero has dimension equal to irregularity, which means is x eta O x eta. So it happens to be equal to the dimension of automorphism group, as we explained here. Right? You see there are some similarities between these. And indeed, there is a natural morphism. Oh, I mean, depends on divisor. So let me explain. So there, let H be an ample divisor. Then there is an automorphism, a map between them. You pick a 0. Oh, this is well known actually. So this set H. The map is given by the following. You have a map, you have a automorphism, and then you map to this to H and minus H. Right? We know they have the same divisor class. So you minus H, you get a numerical equivalent to 0. This divisor is numerical equivalent to 0. Okay. Moreover, if H is ample, this can be defined without using ampleness. But if H is ample, this theta H is surjective. And I don't want to prove here, although the proof is very straightforward. So now we can use this fact. So recall what we have before. We have a divisor B. We know some action of B eta numerical equivalent to D eta, right? This is our choice. We have something here. And the first, let's consider an easy case, assuming B eta is ample. If this is ample, then we have a map theta B eta as before, defined by the following. H maps to H on B eta maps minus B eta. And because it's ample, this map is surjective. That means there must exist a H lives in this automorphism group of X eta. Well, certainly this lives in the birational automorphism group, such that it can map to this B eta. Let me see. Subtract the D eta. Let's do this one, right? such that H B eta minus, oh, let me write here. Yes, this is right. Equal to G B eta minus D eta. You know, from this, you know, it's numerical 0. So this divisor lies in Picard 0. And because it's surjective, there is a H, automorphism H, such that its image equal to this guy. This lives in the Picard 0. And in Picard 0, this is just the equal. Equal means it's linear equivalent. So what we have is, we have H times B eta minus B eta linear equivalent G B eta minus D eta. Okay. Yes. Let me see. Yes, this is what we want. Let me see. Hold on. D8. Yes, from this we know this D eta lies in the cone generated by let me see. Maybe I should change a little bit. Let me see. This B eta equal to how should I make it? I want to cheat a little bit to make it easier to understand. Where should I do? Let me see. Oh, okay, I do it here. So because we want to prove some cone under the action contains D eta, so it suffices to consider it contains G inverse D eta. That's okay. Because this G we can just put here, right? So for this divisor, I just consider D eta minus, I'm not considering this one, consider G D eta, consider this one. Okay, so there is the H here, and I need to consider G inverse. And now the good news is I can cancel out this one. So we have H times B eta equal to G inverse D eta. And now we know this D eta is contained in the cone of birational group act on this B eta generated by this cone. Because it's birational automorphism, you can put it here. Okay, so we do this simple case. This simple case is we assuming B eta is ample. And under this assumption, we know this map is surjective. But now we do the general case. In this case, B eta is no longer ample, but we still want to using this kind of idea. What should we do? We should make it ample, right? And the way to make it ample is to run some middle model program to get a fibration. And this is exactly what we have. So we do some middle model program of B eta because it's Calabi-Yau, so we can just run B eta middle model program. And then it corresponding to a contraction. So in this case, this B eta becomes the Poolbike of ample divisor. So maybe I just write it B prime and the Poolbike BY eta. And this case is ample. And the good news about Calabi-Yau variety is this is still Calabi-Yau pair by a result of Ambro. There is a canonical bundle formula tells you this is a Calabi-Yau pair. So you couple with some boundary, this is a Calabi-Yau pair. And we can work exactly the same argument to know, using the same argument to do a map using this BY82 and in some Picard group of Y0. So far so good. But the problem is we using the birational automorphism group of the base. But initially, we are only allowed to using the birational automorphism group of X, right? So the previous argument allowing to using birational automorphism group base and to rectify the linear numerical equivalent to linear equivalent. But in the Kohn conjecture, in the formulation of Kohn conjecture, we only allow to use the birational automorphism group of the top of this one. So how should we lift the automorphism of base to the top? And this is the most difficult part. And in order to apply this, to do this lifting, so we just put the problem here. We need to do some surge action. So we need to make some surge action. So in order to do the lifting. Some version of this. In order to do this lifting, we need to using the following result of Jinsong Xu. So this is result. Let me just quickly recall it in the following. I think it itself is very nice result. So for a Calabi-Yau fiber space, we consider the Albanese map of this Calabi-Yau fiber space. So Albanese variety, just the Picard zero, the dual of the Picard zero. And this Albanese fibration has a very nice structure. It's almost isotrivial. So it's isotrivial means you take any fiber of this Albanese map, and you take the fiber product, you quotient out a finite group. And the natural projection of this automorphism group quotient out of K is exactly the Albanese map. Okay, let me put it this way. This K is a finite group. This is a finite group in auto 0. And this Albanese map is exactly given in the following form. So you take a fiber product with auto 0, and you quotient out this finite group. This group is act on the diagonally. And the contraction is given by the second factor. So this is the same as automorphism, Albanese map. So the experience, this result says the following: the Picard,
So this is over any field?
I'm sorry?
This is over any field? Because eventually you want to apply.
This is also works in character with 0 and algebraic closed. But it just passes to the algebraic closed field, and then because algebraic group has a good functorial property when you're passing to it's functorially. So we working with generic fiber, but we passing to the geometric fiber. So this result, yeah.
But does it follow? Okay.
Yeah, this result follow from Michael Bryan's result. He has a result about non-affine group action on the varieties. And using this result, Jinsong Xu cook up with this structure theorem. But we didn't using the full version. What we can take from this result is the following. This automorphism group is isogenous to this Albanese variety. Right? This is Albanese variety. This is here. So they are isogenous. Almost the same as Albanese varieties. So let me quickly finish this in 1 minute. So we have a fibration X to Y. And then this is also Calabi-Yau, as I mentioned. So the Albanese map is surjective. And this Albanese map is also surjective. By the universal property, we can get Albanese map from X to Albanese map of Y. And this is also surjective, right? But by Xu's result, we know this is almost the same as auto zero, isogenous to iso zero, and this is also isogenous to auto Y. So there's also a third axial map. Somehow, I'm cheating a little bit, but this convinces you we should do the lifting from the bottom to the top. All right, putting all these together, we can prove the second theorem I want to mention before. All right, I'd rather stop here. Maybe it's too technical on the last part.
Okay. Thank you very much.
Thank you. Let me open.
So, are there any questions? So, are there any questions from online? So, sorry, could I contact the technical and ask a technical question? So,
Oh, sure.
yeah,
Go ahead.
that's yeah. So the result you quote is about KOT Calabi-Yau, right? And
No. It's even weak terminal Calabi-Yau. We can only terminal Calabi-Yau.
But yeah, but the main theorem that you want to prove is about Calabi-Yau fiber space. So how do you? Yes. So could you explain a bit more how you apply? Yeah, how you would apply the theorem?
Yes.
Which is it a relative Albanese map or I don't know?
I'm working with a generic fiber.
Yes.
So
yes.
everything.
Okay, so you change it to the geometric generic fiber.
So this is what I want to say.
Yes.
We prove something like this. We have the bidirectional action on some group, and this part, let me put this way. We should have G. How should I say? The element here is linearly equivalent to a divisor D8. So I get some linear equivalent. And from this linear equivalent, just as a simple case, you threw in the vertical divisor. You will get a linear equivalent of D, of the total space. So what we did here is on the generic fiber, from numerical equivalent, you get a linear equivalent. And then we repeat a simple case to throw in all the vertical divisors to get a linear equivalent of the total space over S. So I'm not sure if this makes sense. So what
how do you get the linear equivalence?
Oh, the linear equivalence is just using this action. So let me explain it. So as an example, I'm explaining here. You get two divisors which are numerical equivalent, but to get the other to get a linear equivalent, we're using linear action to get a linear equivalent. So this is action. This is for example, in the product elliptic curve, you can just using this transformation. You just transform one point to another point. They are the same, certainly, they are linear equivalent. And we just apply this idea to the general Calabi-Yau case. Because for general Calabi-Yau, there is a similarity here. We can using this automorphism group to rectify the numerical equivalence. They have the same dimension. They are so theoretically, intuitively, you can believe all the automorphism group corresponding to a numerical equivalence. So all the numerical equivalence coming from a movable from this auto zero, because they have the same dimension.
Yes, this I see. And why did you talk about this isotrivial theorem? So I wanted to ask.
Yeah, isotrivial is using to lifting, because in the general case, we don't have this surjective map. It's no longer surjective if D8 is not big. Yes. So we run minimal auto program to get a fibration. And here on the bottom, we get an ample divisor. So surjective holds on the level of bottom means on this auto Y, we get a surjective. But we only allow to using auto X because our birational Kohn conjecture is about automorphism of X, not automorphism of Y, right? So that means we need to make sure this automorphism coming from the top. This auto Y we are using coming from top.
Yeah, this
And
is
the other,
what I want to ask. So
Yes.
because the X eta and Y eta, they are both not defined over algebraic closed field. Then
yes,
how?
yes.
Yeah. And
Yes, okay, so let me explain. So first, there always exists this morphism. This is called the Blanchard lemma. This morphism can be defined on the level of non-algebraic closed field. And then in order to show it's surjective, you only need to pass into the algebraic genetic fiber. So this automorphism, you can just, then you just pass into the geometric fiber. You say, you prove this is surjective somehow.
so it's the same, does it compatible? Maybe this is too technical, but just to make sure that this zero compatible with space change over.
Okay. Let me see. This part, actually, this is not what I proved, but let me explain. This may not, this I believe it's compatible, but let me explain what we prove here. We prove the following: auto to auto Y eta, and then we take the Picard 0 Y eta. So this is something from the bottom. And then I need to prove this is surjective. It suffices to prove this is surjective. And this is compatible. I indeed prove it's compatible with base change. So we consider auto X0 and this one.
I see.
Yeah, this could be proved compatible.
Great. Great, thank you.
No problem.
So are there more questions? If there's no more question, then let's thank Professor Li Zhang again. So thank you very much.
Thank you. It's my pleasure. Thank you.